Hi, this video is Ideal Gas Law Part 1. So we are going to take a look at the conceptual basis for the ideal gas law. So please be reminded that so far we have discussed Boyle's law, Charles's law, Gay-Lussac's law, Avogadro's law, and combined gas law. And please remember that again, you have four variables in gases. So you can measure the pressure of a gas, the volume of a gas, the number of particles in that gas, and the temperature of the gas. Now, please be reminded that in Boyle's law, again, we are looking at the relationship between pressure and volume, and therefore, because we want them to be the highlight, we have to keep the number of particles and temperature constant. In Charles's law, remember, it's about temperature versus volume or vice versa. So therefore, we have to keep the number of particles and the pressure constant. And then in Gay-Lussac's law, we are looking at the effect of or the relationship between pressure and temperature. And because of that, we have to keep the number of particles and volume constant. And then in Avogadro's law, we are looking at the number of particles and the volume. So therefore, again, because it's N and V, so therefore we have to keep the pressure and the temperature constant. Okay, so again, it's just an interplay of the four variables. If you want to investigate a 1:1 relationship between variables, so you have to keep the other two variables constant. Now in combined gas law, this is a departure because we are looking at the relationship between three variables. So we are looking at the relationship between pressure, volume, and temperature all together as three. So therefore, we have to keep the number of particles constant. Right? So again, so in combined gas law, we are not investigating a 1:1 relationship between two variables. We are investigating the interrelationships of three variables: pressure, volume, and temperature. And because of that, we have to keep the number of moles constant. But again, if you follow that logic, it's kind of inevitable that what if we invent a law that kind of takes a look at all the variables, the four variables as a whole, and none of those four variables will be kept constant. So we will be investigating the relationship between P, between pressure, volume, temperature, and number of particles, and there will be nothing that will be kept constant. Meaning, in this law, we change the pressure and look at the effect of the volume, knowing that these two are not changing. And that is also the same for Charles's law and Gay-Lussac's law and Avogadro's law. In combined gas law, it's like, okay, what if these three can change, P, V, and T, but N cannot change? So therefore, in the ideal gas law, we are going all out. We are saying, okay, what if we set that the pressure can change, the volume can change, the temperature can change, and the number of particles can change, and nothing is kept constant? Okay, so that's the idea. So that is why we have what we call the ideal gas law. So again, the way to kind of think of the gas laws coherently as a whole is kind of think that, again, these four laws, the first basic four laws, are kind of just picking two variables out of the four and keeping the other two constant. Combined gas law is kind of picking three out of the four. Now, you might be asking, sir, why P, V, and T? Why not P, V, and N, and T is constant? Why not V, T, and N, and P is constant? Well, because it's the most logical one. Because if you think about it, what is N? N is number of particles. So, a lot of times when we investigate, we put a gas inside a container, right? And if we put a gas inside the container, we want that container to be sealed, meaning the container cannot take in more particles and cannot release more particles. So therefore, the most common setup, so to speak, is a container wherein the particles cannot escape from the container, or wherein you cannot add more to the particles in the container. So the most logical setup is where you keep the number of particles contained, because the container is enclosed, or again, no particles can get in and no particles can get out. So that is the most common setup. Obviously, if you want to make your own law wherein it's about a law that is the relationship of N, V, and T and P keeping the temperature constant, go ahead. But again, it's just in the practical sense, it's the only sensible setup where the gas is enclosed, so therefore the number of particles is constant, and it's only the pressure, volume, and temperature that is kind of changing. Now, the ideal gas law is again going all out when we are saying, what if all of the four particles can change, meaning the pressure can increase or decrease, the volume, the container can expand or compress, the temperature can become hotter or colder, and then you can add number of particles or you can take away number of particles inside the container. So that's the idea for the ideal gas law. So again, the purpose for this video is just kind of to orient you to kind of give a bigger picture on how the progression, why we need to study Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, combined gas law, and ideal gas law, and how they are kind of interconnected. And again, it's all about these four variables. These four basic laws takes a look at only two of the four. Combined gas law takes a look at three of the four, keeping one constant, the most logical one to keep constant. And in the ideal gas law, we kind of go all out, and what if everything can change and nothing is kept constant? Okay, so that's the idea for the ideal gas law. In part 2, we will take a look at its implications. We will take a look at its calculations that are involved in the ideal gas law.